Okay, so thank you. And so my name is Herbert Bos. I'm from the VUSAC Systems Security Research Group at Vrije Universiteit Amsterdam. I want to start with the most important information of this talk today, which is that today is my birthday. Yes, thank you. And I would like to thank you all for coming to my birthday, and thank you in advance for all the great presents that you're going to give me afterwards. I don't see them on you, so they must be in the corridor somewhere. Thank you. In this talk, though, I want to talk about threat models. And I want to start with a story that occurred a couple of years ago when we disclosed a vulnerability in Android that allowed attackers that compromised your PC to also compromise your smartphone. And we thought that's really stupid. But some of the Google engineers disagreed. So here's a reaction by one of the Google engineers. And he said, look, guys, your threat model is bad and you should feel bad. And then some of the other researchers in the world, responded to that and said, dude, seriously, I think their threat model is valid and maybe you should feel bad. And I would agree with that. But I don't want to talk about that particular vulnerability. I want to talk about what the Google engineers said and what it means to have a bad threat model and to have a good threat model. Because I think that threat models are amongst the most important things in security engineering because they determine what an attacker is trying to accomplish, what an attacker is able to do, and therefore what we should defend against and what we should not defend against. And we frequently get it wrong because we make assumptions about the attackers and the attackers disagree with our assumptions. For instance, we may assume that an attacker will never be able to break randomization or will never be able to infect a phone after compromising the PC, which is the Android issue that I talked about. Or will be able to use side channels to break a cryptographic key or tamper with the hardware, all sorts of other things. Or conversely, we may think that an attacker always has to do certain things, right? An attacker, in order to do software exploitation, always has to inject their own shellcode or always has to divert the control flow of the program, use some particular form of analysis, and so on. And all of these assumptions were true at some point until they weren't, right? More advanced and more knowledge emerged, and then we realized that all of these things don't need to hold at all. So we got the threat model wrong. So let's talk about threat models. And I think there is perhaps a fundamental problem here. And in this talk, I will start with a very accessible part, right? So let's say the first half of the talk, and then I'll go to some complete gibberish at the end, which may be much more technical. And I hope this is still going to be understandable to at least most of you. So, but to help you along, regardless, I will mark all of these slides that are actually important with an explicit exclamation mark. So if you doze off during the talk, it's fine as long as you wake up for these slides. So let's talk about threat models and you. For thousands of years, this is the accessible part. For thousands of years, human beings have tried to make sense of the world by means of classification and separation of concern. And when I say classification, I simply mean that we distinguish between me and you, day and night, rain and sunshine. And so that if, some quarrelsome youth in ancient Greece would come along and say, "Oh, wait a minute. It's all, it's all the same shit. It's all this, a lot of stuff." Aristotle would step in and say, "Oh, no, that's not true. It's all different stuff." For instance, we have plants and we have animals, and the plants can be subdivided into small plants, medium plants, and large plants, and the animals can be subdivided in those with red blood and those with white blood, and the red-blooded ones can be divided into those that lay eggs and those that give live birth, and they're all different. And of course, the quarrelsome youth in ancient Greece would go, "Ooh," because in those days, there was nothing to put a quarrelsome youth straight like hard science and undiluted truth. Nowadays, of course, our quarrelsome youth knows that science cannot be trusted and it's just an opinion, and you can do your own research by watching YouTube movies. But there were no YouTube movies in those days. And therefore, taxonomy could emerge as a scientific method, and we still use that method today. For instance, when we talk about different kinds of vulnerabilities and exploitation, we have software bugs with software exploitation, hardware bugs with hardware exploitation, and we can subdivide the software bugs, for instance, when we talk about memory errors, in spatial memory errors and temporal memory errors, and the hardware bugs and hardware vulnerabilities in, I don't know, speculative execution bugs and row hammer on memory and so on. And that's really handy because now we can focus our mitigation efforts on one particular class of vulnerabilities, right? So we can try to solve the problem of spatial memory errors, buffer overflows, without having to worry about all the complexity of, I don't know, speculative execution or row hammer or so on. Likewise, we can try to solve, at least to the best of our abilities, the problem of speculative execution or transient execution attacks, without having to worry about, I don't know, temporal memory errors or so. So that's good. And this separation of concern is also something that we've been doing for hundreds of years already. For instance, if we look at the Divine Comedy, Dante imagined hell to consist of 9 layers. And it's a little bit complicated, as you can see, so they later simplified that and it became the 7-layer OC reference model. Wherein, for instance, every layer, the functionality could concentrate on the task at hand without having to worry about the hell below them or indeed the hell above them. For instance, if we look at the 4th layer of hell, also known as the transport layer, Dante imagines sinners pushing really big boulders towards the center of hell or away from the center of hell. And this is known as TCP. And they didn't have to worry about what was going on below them, or indeed what was going on above them. And in fact, they could present boulder pushing as a service to the layer above them. So that's all very good. And I would argue that the abstractions that we have, these layering, are actually fundamental. They're crucial for our need to understand the world and be able to work with the world, right? Because all of the systems that we build are so complex that if we don't abstract away all the details, we wouldn't be able to make any sense of this or make any use of it. So we need them. They're fundamental concept. But if you go and talk to Eric Bosman, our PhD student, he will tell you that it's also exactly these abstractions that are the cause of the problem. So there are cracks in the abstraction, there are leaks in the abstraction that actually hide the vulnerabilities. That's where the vulnerabilities emerge. And that's one of the important slides, I think. So Eric has a point. If we apply that to our 7-layer OC reference model of hell, we see that in the transport layer, these guys are pushing really heavy boulders. That's not a great job. And it's also hot. It's hot as hell. Maybe there's demons flogging you and it's not pleasant. So what these guys may be doing is turn on some music because it's much easier to push boulders when you're listening to the Beatles. But then, of course, immediately some neighbor starts complaining because they don't like the Beatles and they will ask you to turn it down. And what we see here is that something that you thought was confined to one layer is actually leaking into and disturbing some other layer. And this is exactly what is happening in computer systems. For instance, when we talk about side channels. Assume that we have 2 processes, two processes here running on top of some kernel, and maybe one of the processes, the one on the left, is doing some super secretive processing, right? Encryption or so with a super secret key. And that is all fine because these processes are isolated. None of this super secret key will leak to the neighboring process or anything that happens in the kernel leaks to any of the processes because there are impenetrable barriers between them. There's a user kernel boundary and there's memory protection between the processes. So it's fine if you do something super secretive, it will not leak to the other process. At least that is the theory. But in reality, of course, there's a lot of stuff, a lot of resources that are shared between all of these parties. For instance, one of the best known resources that is being shared by all 3 parties here is the cache, some really fast memory that is used to speed up processing. Okay, and let's assume that the process on the left here is doing some super secret cryptography by what is frequently done, iterating over this super secret key. And depending on the value of a bit in the key, it will do something if it's the value 0, and it will do something else if it's value 1. Okay, and what that means is that if the bit in the key is 0, do something else will be executed, and because of that, it will be loaded in the cache, right? So let's talk about the last level cache, which is shared between code and data. Okay, and we have an attacker that wants to steal the secret key. Okay, so if the bit of the key is a 0, the code that corresponds to do something will be loaded in the cache at a location in the cache, at a cache line that is determined by the address of this function. Okay, and if the bit is 1, the code for do something else will be loaded in a cache, also at a location that is at a cache line that is determined by the location, by the address of the do something else code. Okay, and meanwhile, this attacker is also accessing memory. Okay, so that is also loaded in the cache. In fact, the attacker we assume to be accessing memory constantly. So maybe a whole pile of memory, and it tramples all over the cache, so that all of the things that were in the cache on behalf of this process will be evicted. Okay, and what the attacker is doing is simply iterate over each of these cache lines and timing how long it takes to read that memory. Okay, and it will be super fast because it's in the cache. Okay, and then at some point, this process starts doing the encryption or decryption, and it accesses the first bit of the key. And let's say that that first bit is a 1. So it will execute do something else. And because of that, do something else will be loaded into the cache, throwing out some of the attacker's data. So now the attacker is still iterating over all of its entries in the cache, and it will in some chunk of memory, and it will discover that these first 3 are loaded super fast because they're in the cache, and then the next one, guess what? It's slow because it was chucked out of the cache. It has to be fetched from main memory. It takes a long time, so this is measurably slower. So now the attacker knows that this code must have been accessed by the victim. In other words, the attacker can decide that this first bit of the key must have been a 1. Maybe later on, it will find that the next thing that is slow is the other entry, the red entry, and then it determines that the next bit is 0, and so on. So it'll keep doing this until it leaks the entire key. Now, this is a problem, because what I would consider the first law of software engineering is that you don't have to worry about these things. We abstracted away all of this complexity. As a software engineer, just someone who writes an application, you don't worry about what is going on at the much lower levels, at the microarchitectural level in this particular case. Okay, and now all of a sudden, the software engineer does have to worry about that. Okay, we hide this behind an API, and it's problematic for the software developer, because now the software developer has to think about, how does this interact with, some microarchitectural stuff there that I don't really fully understand, and how can I make my code constant time and do all sorts of other things. And it's not just this particular issue, the cache. It may also be, main memory, which is vulnerable to bit flip attacks by means of the row hammer vulnerability. Okay, and you have to worry about all sorts of speculative and or /transient execution vulnerabilities, such as Meltdown, Spectre, MDS, and so on. You have to worry about functionality in the operating system, where some operating system functionality, such as memory deduplication, is really handy to reduce the footprint of your system, the memory footprint of your system, but it can actually be used as a side channel to leak information. I'll talk about that later on. And you have to worry about traditional software bugs, buffer overflows, use after freeze, and all of these things. And you have to worry about physical attacks where people start, measuring stuff at the pins of chips, or, doing EM measurements. All of these things are now a concern for our poor software developers. So here we have our software developer, Aristotle, in this particular case, being a little bit stressed, pondering the futility of life and losing the will to live. And I would argue that what we're doing in security research is try to reestablish these barriers, try and reestablish the boundaries that were unfortunately not a little bit leaky, so we try to reestablish them. This is what we try to do in security research. And the problem is that this may not be possible, because what you do is interacting with all sorts of stuff at the outer layer here. And whether or not something is safe, like your interaction with the cache, is determined by the exact thing that you're doing inside of your application. Okay, and the interaction is super complicated. You need to know what it means at the other levels. Okay, as the quarrelsome youth that said, it's all a bunch of stuff, and you have to kind of know everything about that in order to make this safe. So this is another important view graph, I think. So I think that the security depends on not just on your code being secure, but on all the possible interactions with all the other stuff that is out there. And that is way too much and way too complex to really grok deeply. So the security depends on your code and everything else. And to write secure programs, you kind of have to know about all of the other things. You have to know that there is, this potential cache effect that the attacker can abuse. And that is difficult. And so the conclusion there is that these abstractions that are, on the one hand, essential, fundamental, right? So we cannot do without them because life becomes too complex without them, are also in themselves harmful. They're hiding some of the things that you are actually interacting with. Okay, and it gets even worse, because what we're doing in security research is exactly what Aristotle prescribed, which is to treat some of these things in isolation. Treat different threat models completely in isolation, pretending that there are boundaries between these things. Right? We focus on solutions for, traditional software exploitation, for instance, by, randomizing the memory layout of programs, physical attacks by locking things down, turning off some operating system functionality, such as deduplication, maybe making it difficult to abuse indirect branches to stop speculative execution attacks, and maybe we separate so we partition the cache so that you don't share cache space anymore, and maybe we do some tricks for the memory by refreshing memory so that rowhammer becomes more difficult. We focus our defenses on these partitioned regions, as if there is a boundary between them, but of course there isn't. Okay, in reality, and here my slides stop. Oh, in reality, it's all just one thing, and the attackers will basically use anything from anywhere. So any aspect of the space that surrounds this program can be used to exploit your code. Okay, so the conclusion here is that thinking about threat models in isolation is, although also very helpful and maybe essential, because otherwise it becomes way too complex, it's also a bit of a mistake because the attacker is not bound to your partitioning. Okay, the attackers will not follow your rule and they will just basically mess with everything. Okay, and in what way do they do that? Well, they do it in different ways. So you can combine different kinds of attacks, different threat models, in what I, arbitrarily called three different ways: sequential, concurrent, and symbiotic ways of combining different attack vectors, different threat models. So, and some of this is well known, right? So, sequential combination of threat models, attack vectors is a well-known thing. For instance, what we can do is use one particular attack vector threat model, such as the MDS vulnerability, which is one of these transient execution vulnerabilities, to, leak address space layout randomization. Okay, and once we've leaked the address space layout randomization, we can actually continue with another type of attack vector, which is, for instance, a traditional software exploit, right? So we have a buffer overflow vulnerability, and now that we've broken address space layout randomization, we can use the manipulation of a return address or code pointer in general to divert the control flow to some code that is already in the program. And we have an end-to-end exploit. Okay, so we combine two very different threat models in a sequential manner. Another example is something that we did a couple of years ago, where we use a threat model of the operating system, where the operating system functionality does memory deduplication to reduce the overall memory footprint of the system. So memory deduplication is a neat trick. It basically means that, and this was on by default in Windows 10 and Windows 8.1. So what it would do is, if two processes have exactly the same page in memory with the same content, Windows would, periodically cycle through the memory and decide, hey, these are exactly the same. There is no need for me to store this twice in physical memory. So it would merge these pages, store it only once in physical memory, and give both of these processes a reference to that physical page. So this page would be shared copy on write. Of course, it has to be copy on write, because if one of the processes decides to write to its page, you don't want those changes to also affect the other processes. It still has to be isolated. Okay, that's a very good trick to reduce the memory footprint. However, it has unfortunate side effects, namely that there is a potential information leak possibility. There's a side channel, right? Because a process, an attacker process, for instance, is able to detect that one of these pages has been deduplicated, okay? And the reason why you can detect that is that it simply takes much longer to write to a copy on write page, a page that has been deduplicated, than it is to write to a regular page. If you write to a regular page, you just write to the page and you're done. But if you want to write to a page that is shared copy on write, well, you have to trap into the kernel. The kernel has to say, oh, wait, this is a copy on write page. I need to change the page tables, make a new copy of the page, copy the data over, then return to user space, and then you can write to it. Okay, that's a very lengthy procedure, and you can measure this as a user process. So then you know that your page has been deduplicated, that there's another copy of that same page in another process, right? And that leaks, in other words, that leaks something about the content of the memory content of another process. That's a side channel. It's a very coarse-grained side channel because it's at the granularity of 4 kilobytes. But what we've shown in the attack, in the dedup ex machina attack, is that you can make this much more fine-grained and leak even high entropy data, such as, addresses of code or data. Okay, so pointers, in other words. And you do that by making sure that much of the page is known and only a little bit of the information is missing, and then you do guesses for those pages. And if you see it gets deduplicated at some point, hey, that must have been a correct pointer. Now, once you've broken address space layout randomization, because you now have pointers to code and pointers to data, you've broken address space layout randomization, you can combine that with traditional software exploitation, different kind of threat model, or in this particular case, we've combined it with the rowhammer vulnerability. So we've made sure that there is a fake JavaScript object somewhere in memory with pointers to a method, right? So that we've constructed as an attacker by finding out where there are interesting code. We now have broken address space layout randomization, so we know where there's code, and interesting data, pointers, and we make sure that there's a pointer that points to a regular JavaScript object mapped exactly at a location that's vulnerable to bit flips, using this rowhammer vulnerability. So once you start hammering the memory, a bit will flip, and that pointer to the legitimate JavaScript object will point somewhere else. And we make sure that it points to our fake object so that we can execute whatever we want. Anyway, details perhaps are not even that important, but here we see that we combine operating system functionality, some vulnerability there, with a hardware vulnerability, rowhammer, and we get an end-to-end exploit. And that actually won one of the ponies. Another thing that we can do sometimes is not apply this sequentially, because maybe we cannot do exactly what we want to do with one of the attack vectors, with one of the threat models. So I don't have many. Maybe it's not even a very good category, but we have this attack called tag bleed, where we also break kernel address space layout randomization using two tricks. And the reason is that we cannot use a single trick to break kernel address space layout randomization. So what we do is we use tagged TLBs and the fact that the MMU and your regular code all use the same cache. Both of them have to be combined to break the full entropy of kernel address space layout randomization. So maybe I should not explain this in detail, but kernel address space layout randomization has 9 bits of entropy, so 9 bits of uncertainty. And with each of these tricks, we can only leak a small number of those bits. So the TLB trick here uses the fact that you have a TLB consisting of 128 sets in the TLB. So it's a 12-way set associative cache, and that means and there are 128 sets. And you can very easily determine in what set your particular virtual address is mapped, because the access will be faster if that is in the TLB. So it's a similar trick to the cache side channels. Anyway, once you have the set determined, you have one of 128. In other words, 7 bits of entropy that you leak, and then you just leak the remaining 2 bits with the other side channel. Now, no need to discuss this in detail, but it's sort of, this has to be applied concurrently to break kernel address space layout randomization, and then you can combine it with a software exploit again to compromise the kernel. Okay, so it's 2 things at once. What is really interesting, though, and this is really what I want to talk about, is the last category. It's an interesting category, and I'm not sure how many of these cases occur, but I'd like to see people look for these things. And it's what I refer to as symbiotic combination of threat models, of different ways of attacking a system. And the key thing here is that by combining these 2 different threats, you make both of them stronger, right? So by combining, in this case, speculative execution attacks with traditional software exploitation, both of them become better. So they reinforce each other. And that is unusual, right? So the combination of the 2 is greater than the sum of its parts. Okay. And if you want to know the details about this attack, maybe you should look at the paper, the CCS paper. This is also one that won a Pony award this year. So let's have a look. What I said is we're going to, and I should give credit to the PhD student who actually did all the hard work, which is Anas Göktaş, who's still to submit his PhD thesis, but this is fantastic work at least. All right. So I said that we're going to combine 2 completely different threat models. And one of the threat models is the threat model of speculative execution attacks. So Spectre attacks, which burst onto the scene in 2018. I'm sure you all remember because it was all over the news. There was a lot of commotion about this. And there was even, logos for these vulnerabilities, Spectre and Meltdown, which I never understood why there had to be logos for vulnerabilities. But it's there, right? So, and it's a serious issue. And it's an issue that still to this day has not been fully solved. Right? It's a complex vulnerability to solve. Okay. And there are many different variants of this Spectre attack, of this speculative execution attacks, but only 2 of them are relevant for the talk today. So I'll talk about 2 of them. And one of them is essentially based on what you see on the slide here. There's an indirect branch, a jump in this particular case, to an address that needs to be calculated first. So the CPU has to calculate the address, and then you jump to that. Now, it may be the case that it takes a bit of time to calculate the address, right? So the CPU doesn't really know what the target address will be, where it should continue processing. And it has all of these execution units ready to go, but it doesn't know where to continue. So rather than waiting, which is of course super inefficient, it decides to, speculate. It tries to predict where to continue execution. Okay, and it does that by looking at the past and say that the last 100 times the indirect branch targeted some address X. Well, the CPU is going to say, it's probably going to target address X again. Let me continue, speculatively, let me continue at this address and execute instructions speculatively at that address. Okay, and if I was right, if the guess or the prediction was right, fantastic. We have all of this computation, all of these instructions that we've already executed, and now we can use the results immediately, right? So we can commit the result. If I was wrong, which is of course possible, then I have to revert all of this, and I have to undo all of the architecturally visible effects. But other than that, there's no harm done, because I haven't committed these results yet. I just executed them, kept them apart, and then, waited for this branch outcome to be resolved. Okay. So that's speculative execution, and it's responsible for a lot of the performance of modern CPUs. So it's really important. Okay. Another interesting aspect of this is that the attacker can influence this prediction. Certainly in the older processors, you could, from user space, simply say, let me do an indirect branch myself and execute this for 1,000 times and make it jump to some target address X, right? And then call the kernel, do something in the kernel where there's also an indirect branch that maps onto the same slot in the branch predictor data structure, so the buffers that we have there. And if it's in the same slot, it will predict on the basis of what I trained the predictor to be the right answer. So the user process trained the predictor to jump to some address X, and then you go to the kernel, and the kernel will also think, well, it's probably going to be that target address, which in itself would not be a problem, right? Because it's only executing this speculatively, and it's undoing all of these architecturally visible effects. Okay. Now, this is one of the Spectre vulnerabilities, so it's the one that we see here. It's also, popularly known as Spectre Variant 2 or branch target injection. And it can be a jump or it can be a call, doesn't actually matter. The key thing here is that we cause a misprediction, right? So this is what we do. We train the predictor and we cause a misprediction, and then we make the kernel jump to a trained target. Okay. Another variant of Spectre is known as Spectre Variant 1 or bounce check bypass. And I want to mention this first, and then we'll talk about how we can even use that, the speculatively executed instructions that are going to be thrown away anyway. Okay. So bounce check bypass is doing exactly that. There is a little bit of code that's trying to be secure, so it's doing a bounce check. It makes sure that some untrusted input here doesn't access an array out of bounds. Okay, so it checks whether this untrusted input is within the array bounds, and only then it will do an access of an array element with that index. Okay. And it stores that in a variable data, which it then uses in turn as an index in a second array. Now, the key thing here is that the CPU doesn't just predict the outcome of this indirect branch. It will also predict the outcome of a condition, right? A conditional statement, a conditional instruction. So it will try to predict what the most likely outcome of this condition will be. And if the last 100 times the if condition yielded true, it's going to assume that the 101st time is going to be exactly the same. And it will start executing these instructions speculatively. But it may get it wrong, right? It may be that the 101st time you provided it with an index that was way out of bounds. And in that case, the program will access some memory outside of the array boundaries, some memory that you shouldn't be allowed to access. Okay, and of course this is, only executed speculatively, so the architecturally visible effects will be thrown away, but there is a trace. So there does leave a trace at the microarchitectural level, so at the level that implements the architecture. And to illustrate that, let us assume that this, only for simplicity, is not fundamental. Let us assume that this second array, array 2, is shared between the attacker and the victim, say the user process and the kernel. Okay, and like I said, this is not fundamental. And the attacker is going to make sure that all of this data, all of the elements of this array, are removed from the cache. They're flushed from the cache. Nothing is in the cache. And this is easy to do by just accessing lots of other memory. You make sure that none of these elements are in the cache. This is all not in the cache. Okay. And then you train the predictor to mispredict. So you do the system call many times, making sure that the victims thinks that it's probably going to be true the next time. So 1,000 times you execute this with an index, an untrusted index that is inbounds. So the CPU is going to think, well, next time it's going to be inbounds again. But then, of course, it's not. You provide it with an index that is out of bounds. Okay, what will happen is that speculatively, the code here will be executed. Now, why is this relevant? Well, if the attacker were to access any of the array elements initially, all of them will be slow, right? Because they're not in the cache. We flushed them from the cache, so they have to be fetched from main memory. It takes forever. And this is measurable. Okay. But now, when we execute these instructions speculatively, it will access this element with an out-of-bounds index, and it will load some data that we're not supposed to access speculatively into this variable, and then use that as an index in a second array. So let's say, so all of them are slow. So let's say that it finds some secret data that has the value 2. Okay, so you access some byte in memory, and it turns out that the value is 2. And now we use this data, this value of 2, as an index in a second array that was shared with the attacker. What will happen? Well, not much, right? Because all of this code that was executed speculatively will be thrown away. But the memory access did take place. So we did have an array 2 access with the index 2. And that means that that array element is loaded into the cache. Okay? And that means that if the attacker now starts accessing all the elements in the array, the attacker will find that all of them are, the first is slow, and the second is slow, and the third one, right, at index 2 will be fast, because this is in the cache. Okay? All the others will be slow again. In other words, by looking at which element in the array, which index is fast, the attacker is now able to conclude that the value that was read at this memory location must have been the value 2. Okay, so in an indirect way, you still are able to deduce what the code was doing during speculative execution, the value that it read during speculative execution. Okay, is that clear? Speculative execution, good. Okay, so unfortunately, it's really hard to exploit this nowadays. And there's all sorts of mitigations. You have software mitigations in the form of red pollines, for instance, and you have hardware mitigations and all sorts of other things. And because of this, Spectre attacks are nowadays super difficult. Okay, what about the other threat model? So the regular software exploitation. Well, this is all really well known. We've been doing this since the 1980s, right? So buffer overflows and similar attacks have been around since the 1980s. We have some code, perhaps, that doesn't check whether the bytes that are, arriving from an untrusted source fit in the memory that's allocated for it. And because of that, the program overrides some crucial value, a code pointer, say a return address or a function pointer. And that means that the attacker is able to control where the program will continue execution, right? So you can make this jump to some other address. Now, unfortunately here also, it is difficult to exploit this, certainly for targets such as the Linux kernel. And the reason for that is that you cannot make the program jump to, the kernel jump to, for instance, your own injected code. Code injection no longer works because of the NX bit or, whatever terminology you want to use there, data execution prevention or write exclusive or read. Anyway, you cannot jump to code that you've, data that you've written yourself. Okay, so code injection is no longer possible. So what you have to do, you're forced to reuse code that is already present. In this case, code that is already in the Linux kernel, you have to reuse that. You have to divert the control flow to the code that is already there. It's a code reuse attack, such as return-oriented programming. Okay, but that's also difficult because of randomization. You don't know where these code snippets that you would like to have executed to do your malicious things, where they reside, because the memory layout is completely randomized. And if you're unlucky, it's even using fine-grained randomization. So, for instance, if you're attacking something over the network, this would be really difficult to determine. Okay, moreover, if you're trying to do this on the kernel, if you guess wrong, it's game over, right? So it will actually crash your system. So, in other words, blind attacks on the kernel are exceedingly hard. Blind attacks are possible on some other types of software, and it's really cool work that was pioneered by Andrea Bitau and some of his colleagues. And I just want to very briefly mention this because I think it's super cool. The idea here is that you can attack software with, arbitrary randomization. You may not even have the source. You may not even have the binary. You may not know the binary, right? You have no idea. This may be completely unknown code with unknown randomization. And what they do is they attack this. The assumption is that they find some memory corruption that allows them to corrupt a function pointer or a return address, or actually the paper talks about the return address. And so they can jump to arbitrary locations. Now, almost always this will be an invalid location, right? Some memory that is not mapped or that is not executable, and it will lead to a crash. Okay? But they keep trying. They keep trying until at some point they get, in that sense, lucky that it's not a crash, but it's a hang. And you can distinguish between the two if you're talking about, say, a remote web server by seeing if it's a crash, your connection will close, and if it's a hang, your connection will hang. Okay. And just these two effects, a crash versus a hang, is sufficient to infer something about code that you're executing on the remote side. So they can determine, for instance, that the code that was executing on the server side was doing a lot of pops from the stack, a lot of pop instructions from the stack. Okay, and that is useful because you can construct gadgets for a code reuse attack out of that. Okay, I don't want to talk about the details. If you're curious about this, talk to me afterwards. But it's super cool, except that it works only on a very limited set of software, namely the software that is completely crash resistant, such as certain web servers that have child processes, and if the child process crashes, it will automatically fork a new child process with exactly the same memory layout, so you can try again. So you can actually afford to crash this web server, the processes in the web server thousands of times. Okay? Now, that is true for very few processes, for very few programs out there in the real world. And moreover, you're also banking on the fact that nobody's actually checking the web servers to see, 1,000 crashes. That's a bit much. Maybe we should investigate, right? And finally, it doesn't apply to really high-value targets such as the Linux kernel. You cannot do blind attacks like this on the Linux kernel. So what happens if we combine these two threat models? So the threat model of regular software exploitation with that of speculative execution. Well, now we show that we can do these blind attacks even on high-value targets such as the Linux kernel that cannot afford to crash. Okay. The idea is as follows. We use a regular software bug, for instance, a buffer overflow, to corrupt a function pointer, a code pointer in general, but a function pointer, which will be used as a jump target. Okay, so an indirect branch will be using this code pointer. But we make sure that the code pointer is used during speculative execution, which has a fantastic advantage, namely that if we jump somewhere where there is no code, right, where we would normally crash, we don't crash. It's speculatively executed, so it doesn't matter, right? So you may get it wrong, and it's not going to affect anything. Okay. Moreover, we don't use the fact that we can train this predictor to target a particular address, right? That by training, we can set the target address to some value which no longer works, right? Modern mitigations make this impossible. But now, instead, we corrupt the address that the indirect branch has to target by means of memory corruption. So as far as the CPU is concerned, and as far as the predictor is concerned, it's actually a valid address, right? It's just, obtained in an illegal manner by means of software corruption, but the CPU doesn't know that. So the Spectre mitigations no longer work. Okay. And under this speculative execution, we can just jump around again. So jump around as much as we want without crashing. Okay. And while we're doing this, we can look for side effects. Okay. Look for side effects that indicate, for instance, that this is a code page and this is a data page, and perhaps we can look for very specific code fragments, specific gadgets, such as a regular Spectre gadget that we can then use to leak everything there is in the Linux kernel. Specifically, if we have our two Spectre variants here, and I've grayed out the part that we don't use, we have our, what was originally our our bounce check bypass and our indirect branch pollution, misprediction. So we're going to use variants of this, a part of this, with this one to create something new. So we're not going to use the gray part, but we will use this misprediction on a condition. Okay? And we're going to use this indirect branch also. So instead of the above two, we're going to use this little snippet of code, if we can find it somewhere, where if there is some condition true, right? So if some condition is true, that takes a while to evaluate. This code will be executed speculatively. Okay? But this code will itself contain an indirect call in this particular case. So the indirect call will be executed speculatively, but the target of the indirect call is something that we set by means of memory corruption, by a buffer overflow, for instance. Okay? And that means that we can just jump around with this because the mitigations don't stop it. Before I look at what we do with that, I want to point out that this is a very common bit of code, right? So the 50% of the indirect branches are dependent on a conditional branch within the 50 instructions, and 37 of the indirect branches are within a distance of 5 instructions from a condition. So that means that the probability of there being something, an indirect branch executed speculatively, is very high. Okay. All right. What I said is that we were going to look for side effects that allow us to help in our exploitation. We have, again, a memory corruption that allows us to overwrite some memory, for instance, on the stack or on the heap. Okay. And let's have an example of the kind of things that we can do. Let's say, the page that we see here on the right is something that contains a vulnerability. We can override stuff on this page. For instance, we can override a function pointer. What we do is we overwrite the function pointer with a value, and we then go and look whether or not there's cache activity with this address that we override. So it's trying to jump to some address that we determine as an attacker, and then we go and see whether or not this cache set became active, the cache set that corresponds to this target pointer address. Okay. So how do we do this? Well, so we make it jump there, and we simply see by doing our cache side channels whether or not this cache set became an active cache set, right? Whether something that we put in there was now flushed from the cache, so the access became slow. If this is not the case, it jumped somewhere where there was no code. But if this was a valid code page, that cache set will be active. Is that clear? Kind of? Yes? Maybe? Okay, so I see some people looking uncertain here. So what we do is we're overflowing some buffer or doing some other memory corruption that allows us to, target a function pointer. That is what we're doing. Okay, and we set a value in that that function pointer of some random address in memory. Okay, in most cases this will lead to an immediate crash, right? Because there's no code page there, and that's nothing will happen. However, if there was a code page there, this code will be speculatively executed. Okay, whatever code was there. And if it's speculatively executed, this code will be loaded in the cache. And where will it be loaded? Well, it will be loaded at a cache set that corresponds to the address that we just provided, right? Because that is the code that we're trying to execute. That is the location of that code. Now, how do we determine whether that cache set became active? We know the address there, right? So we know exactly which cache set this is. So we make sure in advance that we put our own stuff in those cache lines, that cache set, and then we make the kernel jump to that address, and we see if our stuff is still in the cache by reading it. And if it's really fast, it means that our code, the data that we put there, is still in that cache set, and clearly no code was executed. If it's slow, however, if one of the cache lines in that cache set is slow, it means that the kernel did jump to that instruction. So there was some code there, and that's now in that cache line. Okay? So now we know this must have been a code page. We guessed the right address. Is that clear? Yep? Okay. So we can do the same thing for data pages. Okay. Oh, and I have to hurry, I see. So we can do the same thing for, and this is enough, by the way, to break kernel address space layout randomization as we have it today. We can just, map out all of the code pages in the kernel, and we've broken kernel address space layout randomization. We can also do this for data pages. So for data pages, we have to do a little bit more effort. We have to look for some code that uses some data that we corrupt. So now we overflow more than just the function pointer. We also corrupt, besides the function pointer, some other memory location. And we hope that there is stuff that, when we execute this function pointer, it will execute some code that looks like this. Something that uses our data as a pointer. Okay? So we again aim to check this particular cache set, and if that cache set was indeed active, in the same way as we saw earlier, it means that some code similar to this must have executed. Okay? Because it's used the value that we put in here, that we corrupted, as a reference in the second, in this instruction, and moved some value to the register Y in this particular case. So it should again lead to some activation in the appropriate cache set. Now, I don't have time anymore to talk about the most complicated one, but maybe that's a good thing. So we can even find super complex gadgets in this way by corrupting data and looking at this one cache set that we use to find an indication that something's happened. So for all of these things, we use the signal that we get on a particular cache as an indication that some code like this must have executed. Okay, in this case, it's a Spectre gadget, and the Spectre gadget can be used to, in subsequent iterations, to leak everything that we want from the kernel. All right. So even just finding the code and data pages is sufficient for many of the attacks. This is even worse. Okay, so what we're seeing here is that we combine the corruption of traditional software exploitation with speculative execution, transient execution, which prevents crashes, right? To come to a better software exploitation, and also the application of transient execution, speculative execution attacks in cases that would otherwise be mitigated. In other words, the combination of these two threat models is indeed greater than the sum of its parts. And I want to very briefly show you the demo of that. So here we see Anas's computer, and Anas's user ID is Anas, and he has a proof of concept code. I hope this is readable, by the way, which he executes. And the first thing it's going to do is look for the eviction sets of the last level cache. Okay, because we use eviction-based sampling of this cache side channel, that the activation of the cache set. Okay, so it looks for the eviction sets, and then it's going to. Oh wait, what did I do? Okay, so this takes a while, and then at some point it's going to look for the kernel code. So there we go. So it's looking for the kernel base address, which it finds after a while. So now we know where the kernel code is. The next thing it's going to look for is some page where we store our code reuse, our ROP payload. Okay, and that takes some time because we have to go through all of these pages. We have to look for data pages and then see which of the data pages are the right pages where we store our ROP payload. So let's see if we move on a little bit. Still looking for the vulnerable buffer. Let me move on a little bit more. A little bit more. And here we go. So after, what is it? Where's the time? 137 seconds, it found the appropriate buffer in the kernel that we actually also control for our ROP payload. And then we are doing some other tricks with the ROP, the code reuse attack, and finally we get root. Okay, great. And so again, what we've seen is that we look for the kernel code pages, then we look for the kernel data pages, so the kernel heap. Then we probe around a bit to look for the appropriate page that contains our ROP payload. Then we find some gadgets that we need, and then we execute our ROP payload and get root access to our program. Okay, conclusions. What I've tried to explain is that the abstractions that we use and that are necessary, that are fundamental, are also harmful because they leak and they are not as solid as we would like to think. And to write secure code, you kind of need to know everything about your code, but also everything about what is happening in the layers below you. Okay, so these abstractions are not actually shielding you from the details if you're talking about security. It's exactly these abstractions that hide some of the things that you should be aware of. Okay, and the attackers will combine these threat models, and what I think is an interesting new combination is the symbiotic combination, where two different threat models, two different classes of attack make each other stronger. Okay? And the combination in this particular case becomes greater than the sum of its parts. Okay, and that is exactly 1 hour, so I should just stop by concluding that the quarrelsome youth from the beginning of the talk was actually right. It's all just a lot of stuff, and the attackers will use all of that. Thank you.